Hi everyone. In this video we are going to cover section 6.3, volumes of revolution, cylindrical shells. So in this section we are still finding volumes using integration, but we're going to develop a different procedure, and that's called the shell method. So in 6.2 we were introduced to the disk and washer method, and where the volumes came from were from taking a region and revolving it around the x and then the y-axis. We're doing the same thing, but with a different approach that allows us to find volumes sometimes more efficiently. Sometimes one method is a little bit better than another. Okay, so where does the shell method come from? All right, that's what we'll do first. And so we have our region in this first picture here. We want to find R. We want to take this region R, and in this example, we are going to revolve it around the y-axis. We did that previously in 6.2 by taking our rectangle and orienting it horizontally with a terrible drawing of a rectangle. But we did that previously in doing the disk method, and it was integrating with respect to y, drawing those rectangles up the y-axis, but using an integral to make the process more efficient. Well, that's not what we're doing in this section. In this section, we are going to keep our rectangle oriented vertically, but we are still going to revolve that rectangle, or the whole region though, around the y-axis. And I want you to think, if you can visualize what shape that would create, and the answer, well, is the title of the section. It would create a cylindrical shell. So we're dividing our region up into these rectangles that, when revolved around the y-axis, form a bunch of shells. And to help with the visual, we have these two pictures here. The one on the left is a single rectangle revolved about the y-axis, creating a shell, a really thin shell. The thickness of the shell is represented by the dx, or the delta x, that we've seen previously. All right, the height of the shell, right? The height of the shell, that is the function f of x. Okay, and then another really important point to in where it comes from in the formula is the radius of the shell, because as you go from the the inside of the region here, this rectangle, whoops, I didn't draw it down to the x-axis. No, I did. That rectangle there would have a much different radius than a rectangle out here on the outskirts of the region. That one on the right, that I've again drawn very poorly, would have a much bigger or would add much more to the volume than the one on the left, because not only is it taller, it's also further out. It's traveling a greater distance as I revolve around the y-axis. Okay, and that radius in our formula that I'll show you in a second is represented by x. Right, it's the distance that rectangle is out from the y-axis. Okay, so here is our formula for the shell method. V equals the integral from a to b, those are the bounds of our region, 2 pi x f of x dx. Okay, so it helps, in my opinion, to see where this formula comes from, and then it'll make more sense as you set these up, right? So this this integral formula, just like in the last section where we kind of saw that area of a circle, a equals pi r squared, here we have essentially the volume of a cylinder. Okay, the 2 pi x, actually let me zoom out so I can show you our cylinder up here. The 2 pi x, that is the circumference of this cylindrical shell as we're going around, 2 pi r, right? And then the f of x is the height of the cylinder. So that is really the volume of a cylinder is 2 pi r squared h, okay, 2 pi x f of x. And then the reason that there's an r squared is really the thickness here is that's the dx. This is a really, really thin cylinder. Okay, so that's why there's a slight variation from the actual volume of a cylinder formula. But if it helps, just like with area of a circle formula that I wrote there, it's 2 pi r h is this 2 pi x f of x. Ultimately, we need to figure out how to take our region and substitute the correct bounds and the function into our volume formula. Let's take a look at the first example here. We have the region R bounded above by the graph of f of x equals 1 over x and below by the x-axis. And so and then they give me the interval also from 1 to 3. So what that means, this graph, under this function, I know we're looking just at the first quadrant, and f of x equals 1 over x does this in quadrant 1. So there's my x-axis, there's my y-axis, this is my function, f of x equals 1 over x. So it's bounded above by the graph, by the curve there, and below by the x-axis over the interval from 1 to 3. So our region R in this problem is this region right here that I'm kind of drawing in red. All right, and we are revolving that around the y-axis. So I'm orienting my rectangle vertically, and then I could try to draw this again. It'll look pretty poor, but you'll get the idea, hopefully. We're revolving this around the y-axis, and it forms this cylindrical shell. Those of you that are artists can probably draw something that looks much better than mine. If you want to see what the whole volume looks like, take a look at OpenStax, and it'll show you not just the region, but it'll show you the three-dimensional three-dimensional volume that you are forming. Okay, so the formula from the last slide, v equals the integral from a to b of 2 pi times x times f of x dx. Substituting in this one is pretty direct. They give me the bounds, 1 to 3, 2 pi. I could have factored that out in front of the integral. I'll do that in the next step. And then x is really just rewriting the x term from the formula. F of x is my function, so times 1 over x dx. We can take the 2 pi out, times the integral from 1 to 3. Do this multiplication here. X times 1 over x is 1, so they cancel each other out, dx. All right, now we're ready to take our antiderivative. The integral of 1, the integral of a constant, is a constant times x. So we have 2 pi times x evaluated from 1 to 3. The substitution in this one is hopefully pretty direct. 2 pi times top bound minus bottom bound. 3 minus 1 is 2. And we end up with 4 pi for our answer, and that would be cubic units. And that is the volume when my red region is spun around and creating a three-dimensional object spun around the y-axis. All right, let's do another example. This one, they give me the interval from 0 to 2. They give me the function, and so I will start out, and we're revolving it around the y-axis. So I will start out by sketching this function, and we can see that it is a parabola because of the x squared, and it's negative, so I know it opens downward. This one starts here. It passes through the origin, goes up here and back down. Ooh, that's not the best looking parabola, but I've never been an artist. Add a little scale here. This is 1. This point is 2. And this height here is 1. And again, we are taking this region, because it says from 0 to 2, and we're revolving it around the y-axis. Again, this problem is pretty direct in terms of substituting into our volume formula. We have the integral from 0 to 2 of 2 pi x, and then the function, f of x, dx. This one's going to be a little bit more involved to integrate. First, we'll factor the 2 pi out. V equals 2 pi times the integral from, it was 0 to 2. Distribute the x, and you get 2x squared minus x to the third, and then our dx. Now we can take the antiderivative, 2x cubed over 3 minus x to the fourth over 4, and that is evaluated from 0 up to 2. Keep my 2 pi. Don't forget to write that every time. Top bound is 2 times 2 cubed over 3 minus 2 to the fourth over 4 minus the bottom bound should just give you 0. And then when you simplify that arithmetic, you should come up with 8 pi over 3, and use your calculator to not make any fraction mistakes, but you should come up with 8 pi over 3 for the volume of that region. And again, if you want to see a better visual of what this region looks like as it's spun around the y-axis, take a look at OpenStax. But the best way that I could describe the three-dimensional shape that's formed is it kind of looks like a bunt pan. If you know what the bunt pan looks like, it's not perfect, but it kind of looks like a bunt pan. So we'll go with that. Okay, so this next rule is just a variation on the last one. If we're revolving around the x-axis, well, everything is in terms of y. So it's kind of the opposite with the disk/washer method. If you're going around the x-axis, everything is with respect to x. The y-axis, everything is with respect to y. And it flip-flops for the shell method. And so it really is going to be helpful to sketch the region, whatever the region is, and draw my rectangle. If I'm going around the y-axis and that rectangle is oriented vertically, well, that forms a cylinder. It forms a shell. If I'm, let me draw my region again. If I'm going around the x-axis and my rectangle is horizontal, that's also going to form a shell. Okay, it's the opposite of what we saw in the last section. So I'll always be direct in which method I want you to use. So you can expect that from me. But sometimes one is better than the other. In the example here, Q is the region bounded by g of y equals 2 radical y. On the left by the y-axis for y, this is like notation for contained in. That's just the interval 0 to 4, and we're revolving around the x-axis. So to start, let's get a quick little sketch. And again, if you're typing these into your graphing calculator or into Wolfram Alpha is a good website, being able to sketch these is a really, really helpful step. So our g of y function looks like this. It's like half a parabola, and then they give me the bounds are from 0 up to 4, so that's the end of our region. So the Q that they define in the problem is this section up here. It said bounded on the right by the graph, so the right side of the region is the graph, and on the left by the y-axis, so the left side of the region is the y-axis. And in this one, we are revolving around the x-axis. So in order to form a shell, when I'm revolving around the x-axis, the cylindrical shell, my rectangle needs to be oriented horizontally. So I am taking my cross-section slices up the y-axis. All right, everything is already given in terms of y, so I'm kind of lucky there. So again, I can plug fairly directly into the formula up above. Our rectangles go from 0 to 4. Our region is from 0 to 4. 2 pi y, f of y is 2 radical y, dy. Simplifying, we can pull out the 2 pi and the other 2, so we get 4 pi out in front of our integral. Bounds are still 0 to 4. And now in order to do this antiderivative, I need a y just in one place. So that's y to the first power times y to the 1/2 power. So add those exponents together. We're not integrating yet. We're multiplying the y terms. We're going to get y to the 1.5 or 1.5 or 3/2. Depends on how you want to write it. So I'm going to write it as y to the 3/2 power. But it would be perfectly fine to write it as a decimal. And then dy. So we can take our antiderivative next, 4 pi. I'm not going to write the integral sign anymore. This is y to the 3/2 plus 1 is 5/2 over 5/2, and that gets evaluated from 0 up to 4. Move over a little bit. Let's see. I want to simplify, and then I'll plug in my bounds. The 5/2 flips up as a, when I take it out of the denominator. So 4 pi times 2/5 times y to the 5/2, and then bounds are from 0 to 4. Okay. Top bound minus bottom bound. Bottom bound gives you 0. 4 pi times 2/5 times 4 to the 5/2 power, and then bottom bound is 0. It's not always 0, but it often is, so it's always important to consider that. And then simplify all of that arithmetic. And let's see, you get 256. So there's lots of 2's. There's a 4 there. There's a 2 there. This is the way that this guy works out. You take the square root of 4. Oops, let me get my pointer. You take the square root of 4, which is 2, and then to the 5th power is 32. So there's 2's all over the place in this problem. But again, use your calculator to do this part. It should be 256 pi over, not over 3, over, let me erase that. Over 5 is my volume. Cubic units. 256 pi over 5 is the exact solution. Our last example for this section involves taking a region and, oh no, spinning it around something that isn't the x or y axis and seeing what that does. Okay, so this is a kind of different problem. You'll see it come up once in a while. It's probably the more challenging part of this section. All right, so let's see. I'm going to sketch my function, x-axis, y-axis, and it says define R as the region bounded above by the graph of f of x equals x. So that's my 45-degree line, this guy, f of x equals x. It keeps going. It's bounded and below by the x-axis, so it's going down to the x-axis, and over the interval from 1 to 2. So 1 is, let's call 1 right there, and 2 right there. So this is the region that we're talking about, and it looks kind of like a triangle, and we're revolving it around the line x equals 1, or x equals -1 rather. So the line that we're spinning around is this green dotted line here. Okay, and I'll come back to what that does in just a moment, but this is x equals -1. Let's first think about how we need to orient our rectangle. So I'm going to shade in my region here a little bit better. Now we're only going from 1 to 2, so it's not actually a triangle. I kind of misspoke there. We're only going from 1 to 2. And in order to revolve around the line x equals -1, right, how do I form a shell? What is its the orientation of the rectangle? And that is going to be vertical. Okay, so I'm going to zoom in on this picture a little bit more to hopefully make it very clear. That red rectangle, when spun around the y-axis or the line x equals -1, when it's spun this direction, will form that shell. That tells me that we are integrating with respect to x. Those rectangular slices are oriented and chopping up the x-axis. So we need our volume formula in terms of x. So this is v equals the integral from a to b of 2 pi x f of x dx. All right, so that's an important step to consider. Is it dx or is it dy? All right, so drawing that rectangle on there I think is super helpful to seeing whether it's a shell or a disc or a washer. All right, now let's talk about substituting everything in. Right? What's different about this problem while we're revolving around a different line? What changes? Do the bounds of the integral change? Well, no, those rectangles are still being chopped from from 1 up to 2. That doesn't change. We have the v equals the integral from 1 to 2. 2 pi, that's just a number. That doesn't change. Then we come to x f of x. First, let's talk about f of x, because that doesn't change, and why not? What does f of x represent? Well, that's just the height of the rectangle. That's this representation right here. Is the height of any of these rectangles changing? The answer is no. The function's staying right where it is. So that gets plugged right in. What is my function? F of x equals x. So that right there is just x. It's this x that I'm going to circle in red that I want to talk about. What does that x represent? I'm going to zoom in on my picture. Come on, zoom in. There we go. That x represents the distance. Whoops. That x represents the distance that my rectangular slice is from the y-axis. That's the radius of that slice. So what have I done by revolving around a different line? Well, I've increased the radius. Let me get a different color here. Bear with me. Let's go with, I don't think I've used yellow in a while. So I've increased the radius. I've made the radius of this slice longer. It went from a radius of x to now I've increased it by 1 unit. So that in the formula becomes x plus 1. The x in the formula becomes x plus 1. Okay, so that's when you revolve around different lines, that's what you've got to really think about. What am I changing about my integral? Am I changing the radius? Am I changing the height of the function? Most of the time in this type of example, you'll be changing the radius. You'll either be increasing it or usually increasing it, but potentially decreasing it. All right, good. So now we can evaluate our integral, and we pull out the 2 pi again. 1 to 2, simplify inside, x squared plus x dx. Now we can take the antiderivative. We get x cubed over 3 plus x squared over 2. Bounds are from 1 to 2. 2 pi times the top bound, 2 cubed over 3 plus 2 squared over 2 minus the bottom bound, 1 cubed over 3 plus 1 squared over 2. When all's said and done, punch the arithmetic into your calculator, and the volume is 23 pi over 3. And again, it's cubic units, but I'll just write it as 23 pi over 3 is the volume of that region. And again, if you go to OpenStax, you'll be able to see what that three-dimensional region looks like. That might not help you with the problem, but visualizing it is, I think, a necessary level of understanding. Finally, we come to not another example, but really just a summary of the 3 methods that we have introduced in these 2 sections. Disk and washer, same formula. It's just whether the disk has a hole in it. If it has a hole in it, you subtract the whole squared, right? So it's integral from a to b, pi times f of x squared, or f of x squared minus g of x squared. Okay, that gives me typical regions, what it often looks like, and typical elements, that's the orientation of my rectangular cross-section. And notice how with the shell method, it flips, right? If I'm revolving a shell around the x-axis, and that's what all these are. I don't have it drawn on here, but these are all revolving around the x-axis. In order to form that shell, I have to flip the orientation of the rectangle, so we're now adding up the y-axis and integrating with respect to y. All right? There is an analogous table that you could kind of draw on your own. You don't need to do this, but that would be for revolving around the y-axis. All 3 of these spin around the x-axis. We could have a really similar looking table for revolutions around the y-axis. But that is it for this video. Thank you very much for listening, for watching. Work on the homework. Let me know if you have questions. Have a wonderful day.